All right, so now atomic orbitals. So basically, one of the fundamental things to understanding the shape of a molecule is knowing how its electrons are sort of shaped around it, these electron orbitals. Before we can get there, we need to remember what an atomic orbital looks like, right? Remember how electrons are organized around just atoms when they're all by themselves. So that's what we're doing with atomic orbitals. So you probably remember these shapes from general chemistry. This is definitely just a review, but nonetheless, electrons live in orbitals. Those orbitals have different shapes. This one would be an s orbital because it's spherical. This peanut guy over here is a p orbital. Because we're sticking with those first few rows of the periodic tables, these are the ones that are going to be the most important. There are also the d orbitals, which look, pardon my inability to draw, look kind of like this, four-leaf clover shape. These are d orbitals, but again, those are only going to be relevant with larger atoms, and we're going to stick to relatively small atoms. Electrons are waves, all right? So this is one of these very odd things about chemistry that was only sort of appreciated fairly recently in our history, is the fact that the electrons actually behave more like waves than they do like concrete particles like marbles. So what you want to do when you're thinking of atomic orbitals is think of it as a cage that that electron is trapped in. That has this phases associated with it. Honestly, don't worry about that. That's weird quantum mechanical stuff. When you move on to your chemistry career and start talking about quantum mechanics, these sort of things become very important. So this table, this little graph right here, is one way to figure out the filling order of these orbitals, right? So each of these represents increasingly bigger s orbitals or spherical shaped. Same with this. And what you were taught to do in general chemistry, and what we're going to review here in a second, but I just want to preface all of it, is to figure out how, given an atom, for example carbon, what are the atomic orbitals associated with it? So what cages are its electrons living in? What are the shapes? So this little triangle is one way to do it. I actually like this periodic table looking thing a little bit better. I think it's a bit of a better explanation. So if we find carbon on the periodic table here, we see that it living in this 2p block. Okay, that means that its highest energy atomic orbital is the 2p. So if I'm going to figure out what carbon has, you're always going to start from the beginning because all of them have the same base. So it would have a 1s orbital. S orbitals can hold 2 electrons, so that would be full. It would also have, going through this block here, a 2s orbital, also full, so that has 2. And then it is spot 1, 2 on the 2p block, meaning that there are 2 electrons living in its p orbital. Okay. So yeah, so you can do this with any of them. Again, things kind of get a little bit weird when you get down here. There are some exceptions. Luckily, we're not going to be down there, so we don't really have to worry about that. And again, this is carbon's electron configuration. And what this tells you is all the different electron orbitals that make up a carbon atom. If we could hold it up in our hand and zoom in real quick, zoom in real fine and actually image those electrons, none of which is possible, but if it was, we would see 2 of them trapped in this 1s sphere, 2 of them trapped in a slightly bigger s sphere, and then 2 in those peanut-shaped orbitals. Another way that you see the same information drawn, so again, carbon we said was 1s2, 2s2, 2p2, is in this, what we call an electron configuration diagram, right? So it's kind of graphed out. What this is sort of emphasizing is the relative energy of each of these orbitals. All right, so the 1s is lower in energy than the 2s is lower in energy than the 2p. The other thing to remember about these diagrams, they illustrate another important point. First off, let's just zoom in. First off, there are 2 arrows in each of these orbitals, or these shells. One of them is pointed up, one of them is pointed down. This is to represent this property of spin for electrons. Yeah, so electrons are kind of spinning around like tops. One's going one direction, one's going another direction. As long as they're moving in different directions, they can live in the same orbital. The other important thing that it illustrates is when we get up to the 2p here, there are 3 different lobes in that p orbital. Each of them pointed sort of different directions. They are all the same energy. So they actually will get half filled by electrons first before you would ever have 2 of them in a given orbital. So if we want to just look at the progression here, nitrogen has another electron with regard to carbon, so that fills up this last spot over there. And then oxygen has yet one more additional electron. Now it will double up within the same orbital. Okay, so these were these filling rules for atomic orbitals that you had learned. One more level of complication here. So again, everything that we just learned was atomic orbitals. That is an atom all by itself. And again, it's like what those electrons look like around that atom. When you start bringing atoms together and they form bonds, those 2 orbitals, we think of it as those orbitals overlapping, but really 2 orbitals come together and they make 2 new orbitals called bonding orbitals. So these 2 electron cages kind of morph together and they'll form 2 new sets of cages, okay? This is very weird. It's very quantum mechanical stuff. It seems kind of stupid, to be honest, but it's how it goes. It's what quantum mechanics decided. And more importantly, the ACS expects you to know it. So we're gonna go over it here. I will say that it's only something that you're going to like topically know until you get much further into your chemistry career and you start doing some of the math behind it, that it will really make sense as to why. For right now, you're just gonna have to trust me that it exists. But so this represents H by itself, right? So a hydrogen atom all by itself. Let's actually just draw it like this. Hydrogen with its 1 electron. So this is what this diagram is representing. Over here, we have 1 hydrogen. Over here, we have another hydrogen atom all by itself. So hydrogen is so small, it only has its 1 s orbital, and it has 1 electron living in there. When those atoms come together and form that covalent bond, those 2 s orbitals morph together to form 2 new bonding orbitals, or 2 new molecular orbitals. One of them is bonding, and one of them is anti-bonding, right? So two atomic orbitals come together and make 2 new molecular orbitals. All right. One of those, the bonding one, is lower in energy. That's kind of confusing. Anyways, looking at the energy scale here, you see that it's actually lower in energy, that bonding orbital. The other one, and by lower in energy, I mean lower than relative to hydrogen all by itself with its 1 electron and its 1 s, right? So there's a gap here, a decrease in energy. A lot of arrows going on. The other orbital that's formed, so one of them's lower in energy than the than the atomic orbitals, the other one's higher in energy, and this is what's called the anti-bonding orbital. All right, so these guys will form together. The reason why hydrogen sticks together is because when it forms this new covalent bond, those electrons get to live in this bonding orbital, and nothing is currently residing in the anti-bonding orbital. If there were more electrons, if I added another electron, it would propagate that anti-bonding orbital. All right, so, but since there's nothing living in there, this is a nice stable bond. Cool, all right. So now we gotta make matters even a tiny bit more complicated and talk about how atomic orbitals will hybridize, okay? So first, make sure you understand how to figure out those electron configurations for an atom.